Hello. Today I'd like to talk about the 2D imaging, also this 2D transformation. So I guess the PA already actually released some specs of our first program assignment. So also there will be some lab session or some sort of video about it. So you can check the KLMS regularly so that you can see what are the available information for you to perform the PA1. So that will might happen near this PA1 deadline. Also, based on based on our current this class attendance, I actually thought about some sort of the tentative schedule. So April 17th on Wednesday, we will have this midterm exam. Before this midterm exam, we can have about 13 talks, also the Zoom session. Right now, actually, we are having this YouTube, this kind of one-way lecture from me to you. But you might have a lot of questions, so probably I will have the Zoom session so that we can have the interactive Q&A session sooner or later. And after midterm exam, I think that we will have about 3 talks, also another Zoom session. Then at the early of this May, 1st, 8th, and 13th, I actually asked the TA to talk about some of the recent technology, NERF, denoising, also this diffusion. So as you know, there are lots of things going on along the diffusion side approach for generating the image and video. So I'd like to give you a chance to what's going on that side. And after that, we will have a late May or also the early June. It's not a July, June. We will have this first student lecture presentation that will be given by you. Also, we will have every talk. There will be some quiz. Also, after that, we will have another round of this paper presentation. So, so you can do the student lecture presentation or this paper presentation by looking at some of the paper. So that's why actually I'm giving you some of the homework to do watching browsing paper and submit some of the summary. And probably when you think about it, there may be, we might have the final exam. Also, for each lecture, we might have some sort of quiz. Then based on that, that will actually substitute the final exam. But anyway, this is a tentative schedule. As we approach this activity, I will give you more information about how we can do this kind of presentation. And these are the today class objective. I hope that by the end of this lecture material, I hope that you can write down simple 2D transformation. Also, one of key message here is we can use this homogeneous coordinate, and also you need to understand its benefit. And then we'll talk about some of the OpenGL related transformation and how we can do the OpenGL API to perform this transformation. And also, I will talk about it at the example of this simple idle-based animation. These actual information are covered in the chapter 3.2 on my the 2D transformation on my book. And you might recall that last time we talked about some of the transformation, actually which is nothing but viewport transformation from the world space to the screen space by passing through the NDC, normalized device coordinate, in the example of this Julia set. Also, you know the PA1 also related to this one. Okay, so we know that actually one of the common example of the 2D geometric transformation is nothing but the mapping point or one place to another one. Any kind of actually geometric transformation can be applied to this vertex that consists of the triangle, right? So also this transformation can be applied to the primitive like the point line or conics and other information. But typically, we represent as I mentioned before, typically we use the vertex or triangle to represent any kind of 3D object for computer graphics. We typically apply this geometric transformation to each vertex of those models. Also, you can try out some of the demo, which is nothing but applying the simple transformation. Let me open up this one. Okay, this very simple image image transformation. So here I actually load this image as a texture, and then I can do the very simple transformation like this here. here translation, I can do the translate. You can see translation. I can do rotation by the putting some value here. This is very simple example, but also if you're interested, you can also go over this OpenGL code, which is available at the homepage, and you can see actually how we can apply this kind of transformation with OpenGL. But I'm not going to talk about all these low-level details, but I'd like to talk about high-level idea here. So basically, suppose that here actually I'm talking about simple 2D translation. So we starting from the x and y. I want to translate those vertex or vertex of this point as an amount of tx, ty. Then we can have this new coordinate x prime or y prime. But also we can represent this kind of one with this simple matrix representation. Given this translation, we can also define the inverse function that undo the translation, which actually can be represented by like this. Also, we can think about it, what are the identity under this translation. The identity basically leaves every point unchanged, right? At that case, it's actually basically if we do this a zero amount of translation, we can basically you can see that this actually identity the transformation under this 2D translation. We can also think about it this 2D rotation. This is actually a very common 2D rotation about the origin, starting from the x and y. You might recall that this is the rotation matrix, right? Cosine, cosine, minus and sine, which I remembered a long time ago. And I can represent this one with r. This is actually the inverse of the r, which actually undo the rotation. This is actually the identity rotation matrix. So we can actually apply the rotation again and again, right? We can rotate the object 30 degrees, which is like this. Basically, initially we assume that object is represented by some vertex like the x and y. Apply 30 degrees and then rotate it, and then another 6 degree, right? Then obviously we can merge this multiple rotation into the one rotation like this, right? This is actually the very well-known property of the matrix multiplication. And here, typically, in the case of computer graphics, we typically talk about this kind of Euclidean transformation, which is nothing but actually applying the translation with the rotation. Typically, this actually we call it also the rigid body transformation. For example, when you do the translation rotation, basically this kind of rigid body doesn't change its shape, right? So the main property under the Euclidean transformation is that we can preserve distance between two vertices of rigid body even after the transformation, also preserve the angle and so on. So then there could be the many different ways of representing this common Euclidean transformation. This is one representation. Here, starting from the x and y, we apply the rotation, and then we do this kind of translation by applying this addition along this vector representation. So, but actually, this is not the common representation that we are using for the computer graphics, mainly because that it actually has this kind of problem. In this case, the rotation and translation actually kind of handled in a separate way. So basically, typically when you do any kind of computer graphics application, we typically perform a series of rotation and translation to place objects that are defined in some place into the world space. But actually, if you're using this kind of separate entity for the rotation translation, it's very complicated. So it turned out to be it is inconvenient, inefficient. Also, sometimes also we need to do the inverse transformation. Then obviously with this one performing inverse, computing inverse, it's very complicated. So that's why we typically we wanted to represent the new representation that somehow represent the translation and the rotation together. In other words, how we can represent this translation into this matrix multiplication. To do that, we typically introduce this homogeneous coordinate. This is nothing but basically, even though we actually think about it 2D plane, suppose that in this basically we represent the triangle vertices in this 2D space with the x and y coordinate, but we can treat it as another 2D plane as a subspace within this 3D space. In this case, somehow by introducing new coordinate, in this case g, we can actually embed this 2D plane within the 3D space, right? and then this G we call it homogeneous coordinate. So any we can use any planar subspace. We typically embed this the 2D plane in the 3D space by setting the G is equal to 1. So basically, in this case, in this homogeneous case, our 2D object x and y also has this G coordinate by having 1. This is actually homogeneous coordinate in the 2D case, and then in this case, basically we can do the rotation with this cosine. If we do the rotation, if we multiply this matrix with this 3D vector, cosine x minus sine y and tx1, which is basically adding tx, right? You can see that by having this one, we can actually transform this translation operation, which actually perform in the vector addition into this kind of the matrix multiplication by having this one. And then another one, and then we have the 0, 0, 1. We cancel this, and then we have also the passing 1 to the here after this the new coordinate after this transformation. Then the modified rotated translate the new coordinate has the x prime y prime with 1. Still after this transformation, this is also in this homogeneous space. We also typically call homogeneous space by having the G equal to 1. This is actually one of the benefit of utilizing homogeneous coordinate. So then, with this kind of homogeneous coordinate, we can also think about scaling. So this is typical scaling operation. We actually some sort of scaling factor along the x, also this y along the y. Basically, we actually scaling down into half. And then in the case of homogeneous coordinates, actually we applying the uniform scaling factor S and S. With the 1 here. Basically, typically in the typical case of this transformation in the homogeneous space, we typically have the 1. So the scaling operations. Also, the last time we talked about the viewport, the simple 2D operation, 2D transformation. It's nothing but mapping given the world space coordinate, we actually transform into some coordinate into the NDC space. We had this kind of the one, some derivation, but we can also represent this one with this matrix multiplication. This rotation, basically this is a multiplication. This actually scaling factor, which actually we are applying the a here, right? So that's why actually we had this term, and also this actual translation addition part. But actually by multiplying this one with 1. It will be actually we can represent this translation with 1 matrix multiplication. Also, this turn out to be conceptually simple. In the end, this one mapping to this one by utilizing homogeneous coordinate here. This one. Shearing. This shearing is a common operation. It's a push thing sideways. In this case, we actually push these things like this one. So that's actually we got this kind of some term here. This actually shearing along the x-axis, and then this the shearing operation along the y-axis. So that's why actually we got this term here. Also, we can think about reflection along the x, and then we got basically we have the -1. In other words, actually we negated y direction. Also, this another reflection about the y-axis. So actually, we negated this -1 along the x coordinate. This is the common, the typical the 2D transformation. So we can also apply the multiple transformation, right? So basically, we can think about it as compositions of the 2D transformation. Everything that I talked about here apply to any other dimensions. But here, starting from the V1, vertex 1, we apply this S actually the scaling, and then we also do the rotation, right? So basically, then if we applying them together, starting the V1, we apply the scaling, and then we rotating them, we got the V0, right? And then we can also this example, we can do starting from the original coordinate, we do this scaling, and then we do the rotating, right? And then this one, since the matrix multiplication is the associative the property, we can combine them together, right? And then we can multiply, and then we can actually make the new matrix then we can actually directly this is matrix that is corresponding to the RS. Then we can, by applying this one matrix to there, we can get the same result. Then performing the scaling and also the rotation. We all know that, but I'd like to actually review these operations. So that's why when you do the multiple operations, multiple transformations, we can combine them together, and then we can do the one matrix multiplication. That way, we can more efficiently perform various transformations with to realize any kind of computer graphics application. And then sometimes we need to do the inverse operation. Obviously, just inverting this matrix, then we can do the inverse operation. Later on, we'll talk about in what case we might need an inverse operation. So obviously, transformation order is different, right? Obviously, we don't want to change this to SNR here, right? So we know that actually scaling, rotating scaling have the they will have a different result. Basically, the matrix operation is not cumulative. In general, we can think about it. This kind of more general set of the transformation we call affine transformation. Basically, starting from x, y, and 1, and then if we apply this kind of the matrix here, there's some arbitrary number for this and this second row, but this third row actually has a 0, 0, 1. Then it will actually the mapping to the another new coordinate in the homogeneous coordinate, right? Then we call it this actual affine transformation. Typically, some of the example of the affine transformation is that any kind of combinations of translation, rotation, scaling, reflection, and shearing. And this actually typically what we actually perform in the typical computer graphics application. In that case, is parallel lines are preserved, also finite point mapped to finite point. These are some of the mathematical property that actually we observing under these affine transformations. Also, there are if you look at the OpenGL or DirectX or any kind of the library, you can typically find any kind of matching corresponding API function. In the case of the OpenGL one, the GL translate, GL rotate, GL scale is available. So typically, in the case of the translate, GL translate the amount of the translation x and y, g. Here actually we are talking about also this. We actually define the 3D space, but actually even at the 3D space, we can also introduce the first coordinate of the homogeneous coordinate. So even though actually in this case we are not showing any matrix representation, we do not in the case of OpenGL API, they do not receive the matrix represent. In this case, OpenGL internally use the matrix format. So in the 2D case, we use this 3x3, but for the 3D case, x, y, g, we introduce 4x4 matrix internally by having the first homogeneous coordinate. So there are many other libraries like GLM, stands for the OpenGL mathematics that can do the various kinds of matrix operations. The rotate amount of the degree and along the rotation axis, and so on. So this is another example of the animation, idle-based animation. Let me actually play the demo. I think they are already there. Let me play this demo. I think that. If I click this one, then I have this one. If I click the left button, it will rotate, and then if I click the right button of mouse, it will stop. I can actually make it big, and I can actually do this one. So when I do nothing, it just keep rotating, and then if I click the right button, it will stop. Very simple application. Okay, so here I will just talk about some of the basic OpenGL function. This main display function. This main display function is nothing but just draw the actual rectangular shape. This actual rectangular shape is defined under this NDC space. This grect is nothing but drawing the rectangular shape. It actually this kind of information. I cannot remember exactly what are actually the parameter. This might be the x and y and width and height, or the two coordinate of the bottom left to top right coordinate. I mean, I don't know what might be the parameter, but actually if you're interested, you can actually Google it. But this is nothing but just the representing the asking the drawing the rectangular shape, and then GL color actually setting the color RGB. So this actually everything is 1, so RGB is every full, so that's why we got a white 1. And then here we rotating, right? So here we GL rotate as an amount of spin. Actually, we change this spin at some at other cases. So as an amount, so basically we rotate the box as an amount of this spin. This is actually rotation axis x, y, z. Basically, the g axis actually when you are looking at the prior OpenGL cases, then the coordinates this x and y and this g. So along the x, y, z axis we rotate. That's actually rectangle shape rotating like this. And then initially we actually GL clear. Also there actually initialize this some sort of the so we are looking at the image, right? So basically we initialize the buffer, which is called with the frame buffer with the color. We actually initialize this color buffer. The frame buffer may have a different component, but actually we clear this the color buffer. Initially, when you actually call this one initial OpenGL maintains some sort of initial matrix. This could be the identity matrix. So OpenGL internally maintains some sort of the transformation matrix. Initially, it has the MI, and then here actually we call it the push matrix. Actually, basically we push the current matrix, the OpenGL maintain current matrix. In this case, MI initial matrix. We put this matrix into the stack buffer here, MI. And then we call it another GL rotate, right? Then we actually apply. In this case this OpenGL create this rotation matrix and then apply into the current matrix. Then we can actually handle this in the case of this initial matrix identity. Then current matrix MR. Then we call this the rectangular shape. Internally it creates some sort of triangle and vertex with this kind of one. Then to draw this vertex triangle, we apply this current matrix, which is nothing but MR, this rotation matrix into that vertices. Then we can see the rotating matrix. Then here we actually perform the pop matrix, and then we store this initial matrix here. Then we pop this matrix and reset the current matrix with this MI. So once we are done, we actually cancel the rotation, the matrix. So then here actually our current matrix turn out to MI, which is actually the initial one here. This is actually typical setup the programming style that we are doing with this kind of transformation within this OpenGL. And the GL swap buffer, later on I will talk about what it means by. Also here, okay, frame buffer. So when you run this one, we are seeing the image, right? So that's why basically this image contains the frame buffer. That's called frame buffer. Frame buffer contains the image for the final visualization. It can have the multiple components. It can have the color buffer, RGB, also depth buffer. The depth, the G value. We will talk about why actually is required. So typically the buffer is nothing but an array. Then actually our monitor projector access the buffer content and then just visualize it, the buffer content, the array content into the screen. Initialize GL color, the color buffer within the frame buffer. We can set the clear color by setting the new initializing value. Also, we can call the buffer creation by calling the GL unit display mode, GL UT double. Basically, it has actually the double buffer with each buffer has the RGB component. And then typically we are using this double buffer, and then we typically perform this swap at the end of this display function. We call this swap buffer. This is let me explain why we actually have double buffer. So if you are just using this frame buffer, then you might recall that. So then in the case of Julia set, we just using only single buffer. So then in the Julia case, actually we are drawing something for buffer, right? So then the writing, computing that value and writing the color for the buffer takes some time, right? But actually our display actually access this buffer content very fast, maybe the more than 30 frames per second, right? Then we can that's why actually if you call our first the Julia set example, you can see that actually this drawing process, right? Since actually we are showing the drawing, the writing down the color value actually takes more slower than this refresh rate of this projector or this OpenGL application. So to avoid that kind of showing the drawing process, we typically using the two buffer. So basically, when you're using the double buffer here, we have two buffer here. Then initially we actually let the monitor to access the projector or the monitor to access this buffer. Then basically nothing there, nothing going on here. Then you can see the static image. While meanwhile we actually computing this value, right? Once we are done on this writing down whole buffer, then we swap buffer. It means that we let the monitor project to access this one. So at that case, once we filled all this one, then the computer monitor to access this one. So then we can get the static image here. Then we also then next time when you call this function, we actually writing this one. And once we are done, we can keep swap this. That way we don't need to show the middle of this drawing process. Basically once we are done, we only show the final image to the monitor or the projector. That's the main. That's why we are actually using the double buffer. That's why we typically call this GR swap buffer. Okay, and okay. So as I mentioned before, the OpenGL maintains matrix stacks. It can provide pop and push operation. Also, sometimes convenient for transformation operation. Also, there are multiple stacks actually. I'm not going to talk about detail right now. So actually, by calling the matrix mode, you can actually set the typical the stack mode, model view, projection, texture, blah blah, and so on. You can see there. I will talk about some of them later on. Also, I will show that we can actually do we can actually maintain, we can actually update this matrix stack by calling the GL push matrix and pop matrix, as I mentioned here. So also we can create the matrix operation by calling this one GL translate, GL rotate, multi. We can even you can also directly provide this matrix by using this multi matrix. This when you call this function, we can actually concatenate with this kind of matrix, rotation matrix or some other matrix with the current matrix. So that's why actually when I mentioned this one, so when I call this rotate, I create this rotation matrix, MR rotation matrix, and apply with this current matrix. But also sometimes we can reset the current matrix, right, by calling the GL load matrix or the GL load identity, and then this override the current matrix actually. In the case when you are using the matrix in OpenGL, typically we are using the column major ordering. So when you actually when you specify the 16 value, basically it has the column major M1, M2, M3, M4. So this actually another kind of the reverse to the typical C convention. So basically we create the array in the C with the I and J. Typically basically this row I and column J. So actually this actually row major one. So to avoid this kind of confusion, it's better to declare this just the 1D array, 16 array. Then basically you should know that we treat OpenGL actually treat this the 1D array like this as the 2D representation, 2D matrix. Also, there are many other types of the matrix operation, but I'm not going to talk about this one in detail. But anyway, main message is that when you develop this kind of graphics application, we need to deal with the transformation matrix. That's why we talk a transformation operation. That's why we are talking about them here. So let's get back to our animation. basically the animation is nothing but we just draw something and then we swap the buffer and then we draw again and swap buffer and so on. So basically the typically is desired to provide more than 30 frames per second FPS for interactive application. So I know that some of you may use the very high frame rate with a very good monitor with high FPS. Then obviously you need to actually provide more faster operation to maintain to provide a very high quality the video and also experience to that at the monitor, right? But here actually we are just using a very simple very simple animation based on the idle callback function. Callback function is very common operation, but I will actually talk about it here. So let's get back to our example here. So when I click the left button, it rotating, right? It's so fast, that's why actually it actually having this shape. But actually when I click the right button, it stops, right? So when I click left, it just keep rotating even though I don't do anything, right? So here, basically when I click some button, basically the OS identify basically there are some sort of our program running on top of this, in this case Windows or some OS, right? So our typically the CG operations, let's say the CG applications running on top of the OS, right? So when you click the mouse, OS actually know that actually the mouse button clicked, right? And then OS actually send that message to this currently active applications. So then, how do we actually let the message to our application? In this case, actually, we do that through the callback function. So actually, I already registered when the mouse button actually clicked. Actually, I got that signal from the OS by saying I actually asked the OS to call this function, mouse function, when the mouse button clicked. So that's the callback function. So this actually callback function, this function call back when some sort of mouse button clicked. So this function comes with some parameter, button state and x and y. This button is which button actually click left. In the case of the left button click, then actually also this left button is down. Then actually I set the GLUT idle function. This actually callback. We actually register another callback function. So we actually register spin display when as this idle function. It means that nothing happens, nothing going on the CG. When, in other words, my application idle, I ask the OS to call this function spin display. This is nothing but this is this is actually spin display. And then when I click the right button with the state of this GLUT down, then I actually actually register nothing into the idle function. So that's why this function is not called. So then what we are doing in the spin display, in this callback function, nothing actually happened when I click left button. When I click left button down, then I actually adding spin value. Here finally we actually change spin value here. We adding 2 degree. Once the spin degree is more than the full degree, then we actually reset with the 0. And then we call this GLUT post display. It's nothing but when we also let the OS nothing going on, just redraw basically redraw the my screen. At that case, actually again, obviously this is another callback function. I already register when I need to redraw my screen. I will register this display function as this callback function. So that's why when I actually change when I actually reduce down my window, actually I can still redraw my one by, since I already registered this callback this function as the callback function when I need to redraw this one. This kind of callback function is very common scheme for any kind of the Windows program, also the many other related OS. That's why I spent some time to explain this concept. Okay, so I already talked about this one, and also I actually discussed with this one with whether this kind of idle-based approach also available in other cases. I asked it with ChatGPT and said that chat animation with the callback function also used in Android application when you are using the OpenGL ES embedded systems. Also, I noticed also JavaScript also using this kind of concept. I double check with the Google search. So basically, if you actually want to know what are the recent OpenGL or OpenGL ES code, you can also ask the ChatGPT to translate this code. I found the ChatGPT is very good at it. Okay, so that's it, and then by now I hope that you can write down to this simple transformation with the homogeneous coordinate. Also, what are the potential benefits, and then also I talked about some of the OpenGL related transformations of the API. Also, I talked about the idle-based animations method with the callback function scheme, and then these are actually our weekly every class the homework. Go over the next lecture slide before watching the YouTube video. Also watching some of the figuration top tier video paper and some summary before the Monday class. Just the one paragraph English Korean is okay. Also when you actually have I noticed that some students are very active. Write down some question at KLMS. That's fine. I will. For those questions written in the KLMS, we will try to answer them. And then I also know that there are very reserved students. Then I encourage you to write down the questions through that online submission that are available at this course homepage. So you don't need to try to come up with a very fancy one. Just write down the very natural, just common questions that naturally arise to you. And then at least you need to submit 2 times during the whole semester. And next time we'll talk about 3D transformation, and that's it. See you next time. Bye.